is the new symbol that we're going to see. So let me just, so if we had velocity equals distance over time, then angular velocity equals 2 pi times the radius over 1 period, 2 pi over t. Okay? Or if we express it in terms of frequency, remember frequency was just the reciprocal of period. So it's most often expressed as both of these are valid. I'm going to purposely leave the unit out at this point. Angular velocity is expressed in radians per second, but you guys
We did radians.
did radians?
Yeah.
Oh, cool. Not everybody? Okay.
No, she did.
It can, because okay, cause the way they get around using radians in the grade 11 IB SL physics, because it's not assumed that that's something that you'd understand or have learned at this point in math. They get around it by saying that the angular velocity is just the circumference over time, but really what the angular part of angular velocity is referring to is the 2 pi radians in terms of the angle that it takes to go once around a circle, because you know that 360 degrees is related to 2 pi in terms of radians. Okay, but we don't really need that at this point. But just for now, I guess we'll just make a note. Yeah. Oh yeah, so now instead of centripetal acceleration, if you want to figure out the object's acceleration at any distance from equilibrium, it's just a rewriting of the centripetal acceleration equation. So we'll start there. Where did I do T or F?
So you did that one.
F squared, yeah. Now, if instead of r radius, we use x in terms of the distance from equilibrium, sorry, I got it backwards. Yeah. I forgot the R in here. Sorry. Sorry guys, something wrong. Guys, I'm sorry, this is the first time using this version of the note. There is no R at this point. In angular velocity just refers to 2 pi over t or 2 pi f. I had the second one right. Okay. We're just going to leave it as 2 pi. At that point, it assumes the radius is 1. That's why it's giving you the angular velocity. All right. subbing in x again because instead of talking about the radius of a circle, we're talking about the projection of it. So we're talking about the distance from equilibrium. So I'll just make note. That's right. Distance from the yeah, that's right. But from the projection from the circle moving, yeah. So it's just the distance from equilibrium point, the middle of the circle. Sure. Now look, we've got 4 pi squared f squared. What is that in terms of omega? We have 4 pi squared f squared. If omega is 2 pi f, then what's 4 pi squared f squared?
2.
Omega squared. Yeah, that's exactly it.
Wait a sec. Just be on my side.
We got to put one more thing in here. Because if we're talking about centripetal force, acceleration is constant. But when we're talking about simple harmonic motion, the acceleration is always going to be negative to the restoring acceleration, based on the fact that the force is directed back to the equilibrium point. So, one last thing we have to do. That's the final version of that equation. So this is to calculate the acceleration of an object undergoing simple harmonic motion at a certain distance x from its equilibrium point. Okay. Now, if we want the maximum acceleration, that's when x is at its maximum. So we have to get comfortable using capital A representing the amplitude, which is the maximum displacement from equilibrium. And it's just a simple sub in capital A. So A max we're just letting capital A be the maximum extension. Yeah.
R is the radius of the circle.
Yeah. X is the projection of that circle. Watch this. I'll go back to that. No, it's all right. I'll go back to the. So I can't pause it, unfortunately. The projection from the middle of the circle right here is this equilibrium point. So if we freeze the projection of the circle going the x direction of the circle at any point, x is the distance from the equilibrium point to that circle's projection. Okay, that's where it's a little different than circular motion.
And that is just the R.
No, the equations still hold true because you could visualize it as the circle actually shrinking and expanding, okay, to a dot. Just trust me on that. The equations still work if we just substitute in x for r. Okay.
Smaller amplitude, the left axis less than the radius, because it's a smaller circle.
What he said if you do picture, what's the